You know, in additive manufacturing, one of the beauties of the technology is it's possible to make enclosed structures that have very complex structure inside. And part of that complex structure can actually be void space, tactically used void space. I'm with Dave Krzeminiski. He's Senior Additive Manufacturing Consultant at EOS. Dave, you've developed something called digital foam here, and tell me about that. How does that relate to this idea of a closed structure with a complex internal structure?
For sure. So traditional foam, we think about it as some material, then there's some gas that's kind of enclosed in that. So you get a porous material, which gives you the light weighting or buoyancy or other features which you're looking for. And if we think about a 3D printed lattice structure, it is essentially that same structure, that same concept, just a little more zoomed in. So we have cells in the same way that a traditional foam has cells, and then we have beams or struts in the way that you maybe would see walls. And what's really great is with these beams or struts, you can be much more prescriptive or purposeful with where you put that mass, where you put that strut for it to perform the function which you're trying to sort of engineer for.
Well, it's interesting as we think of conventional foam, where you might say engineer a shell then inject a chemically reactive foam. So we're looking at a distribution of void spaces, sort of controlling the size of bubbles in a liquid. In this case, if you can actually plan every individual strut, is this the idea of like a Warren truss or an engineered lattice structure, but in 3 dimensions?
Yeah, I mean, with computational design softwares really advancing the way they are, and really lattice structures growing as well, you can really tune how you want this 3D structure in lattice to look. You want it to be very uniform and monolithic, or highly variable, or even kind of hybrid. So depending on, again, the application or the function, you could have, a different surface level lattice compared to a body lattice, or even a certain depth or thickness where you have a lattice. You can even gradient that lattice. Again, you should kind of be hearing that you can, whatever you can kind of design from a software side, there's certainly going to be limitations with how small you can print or how large of a part, right, just with any kind of additive technology. But really, if you can create that design and process that design with the software that goes with additive solutions, you can print pretty much whatever you can come up with, and that complexity is really free. So you're not going to pay a penalty necessarily for having a more complex or more customized design. A great example here would be with this hockey helmet. So we have partnered with Bauer Hockey to bring their liner concept to life, and this is a customized solution. So you can actually head scan or take a scan of someone's head and customize the fit to be more comfortable. And then also you could think about, you could purposely orient any of the lattice beams or features to be purposeful towards any kind of hockey injury or any other purpose which the athlete or the end user would want.
That's an interesting concept, because so you could have a highly anisotropic kind of part, because in many cases, in a lot of engineering examples, we'd like a certain amount of, say, torsional rigidity, but we still would like some flex in an axial plane or something. Yeah. Is that what we're talking about here, highly anisotropic properties in this shape?
Yeah, it could be. What I find very interesting is often when you use a traditional foam solution, you're engineering to maybe the most critical feature or the hardest portion that you're engineering for, and therefore you're over-engineering for other features, right? We think about a helmet. Let's say that there's a specific impact that happens to the top of the crown that you have to protect against. Then you engineer that component for that, but then all the other foam and all the other areas is really over-engineered. It's excess weight. It's maybe kind of necessary. Where this, you can be, again, strategic with where and how you place what you're building, and as a result, again, you can have a more lightweight structure, or you can just put that mass however you want. So it really gives more control to the engineer, to the designer. I think it opens up the conversation you can have around the part you're making, as opposed to being forced to kind of work within traditional boundaries or guideposts. You can kind of explore those areas, and in some ways challenge what the existing design even looks like. Does it even need to fit that current CAD shape? Is that feature really designed because of a traditional manufacturing method? How can additive unlock some of that? And in some cases, maybe even print your whole design for you, consolidate many parts that you traditionally would make individually. And so these are ways in which additive, I think, can really open the eyes and really push the field in terms of what can be done.
Now, it's stronger, lighter, safer safety equipment in sporting goods like that helmet. That makes obvious sense for an application like this. We're standing under a basketball hoop for a reason. I understand you have a very interesting demo here of just basically what you can do with this.
Yeah, so what you see here, the Wilson Airless prototype basketball. Hopefully you can see it in the camera. It is see-through with a lattice, completely airless, which is great. And I think in some ways what our whole team was able to do, all of our kind of collaborators, in some ways this looks so elegant and simple that it maybe seems so obvious, but really there's an incredible amount of engineering that went into what this structure does, how it's printed, and really, again, the number one question we get, does this bounce? It does. You can try it, Jim, here if you want to as well. But Wilson did an incredible job of not just creating a part, right? This is not a part that just sits on a stand during a trade show. This is an experience, right? People can come here, they can shoot, they can dribble, they can dunk, and I think it makes additive manufacturing can be a little scary and overwhelming for some people, and I think this is an object, it's an application where really it opens up the idea of what can be done, but it's comfortable to people to sort of approach it. I mean, everyone's dribbled a basketball in their life, and what's fun is to watch everybody be their own kind of critic with it, right? Everybody looks at it, but everybody, no matter what, they get it in their hands, they go quiet, a little speechless, and they just start smiling, which is pretty incredible to see everybody do that. So,
sporting goods, an interesting application for a very high-tech process at EOS. At Rapid TCT 2023, the air was electric. The excitement about manufacturing in America is palpable. New technologies, new ways of implementing additive manufacturing, not just for prototyping, but as a true production process, were all over this show floor. The future looks very bright for manufacturing in America based on what we have seen here. Thanks for joining us on the show floor. See you next time. Today's episode is brought to you by Engineering.com, a globally trusted source for engineering content. Check out this and many other exclusive videos for the engineering professional found only on Engineering.com TV today.